So yeah, thank you for everyone who showed up. And thank you for everyone who sent through some solutions to last week's homework. I thought it might be a good idea to sort of at least recap some of the concepts that we covered last week and get refamiliarized with some of the equations, because we're going to be expanding on these in an arbitrary number of dimensions. So we're going to be moving from bonding curves to bonding surfaces, and then bonding volumes, bonding hypervolumes, and so on. Why isn't that started changing? Here we go. Okay, so one of the homework tasks that I asked you to think about was to basically show that you can generalize some of these, these equations into any number of steps by essentially piping together the same function over and over again. So this is, for your recollection, delta Z is the number of liquidity pool tokens that are being issued, and delta X is the amount of a certain cryptocurrency that you're providing to an existing reserve inside a liquidity pool. And we use the subscript P here to denote the pool, T to denote the total amount of liquidity pool tokens that exist. And delta X doesn't get a subscript because that affects both the user and the liquidity pool. So starting with this, create this equation. It's not too difficult, and Curious Rabbit actually had, I think, the best solution. I've got a slightly worse one prepared, or at least one that skips some of the steps at the back. But if you guys ask Curious nicely, I'm sure that he'll show you his his work. So all I'm going to do here, in order to make the solution a little bit more intuitive, is I'm going to be changing delta Z, or generic delta Z, for each one of the steps to denote the specific token that it resulted from with its subscript. So this step, because we're actually adding the X token, whatever that is, I'm going to be denoting this delta Z with a subscript X. And what this means is the next token that we're going to add to the liquidity pool, let's call that token the Y token. The total number of pool tokens that exist has now gone up by whatever this number is. And that's really the key to this solution, right? The rest of it is pretty trivial after that, albeit a bit tedious in some cases. So from here, the only thing you have to do then is basically substitute delta Z sub X with the solution here to try and get rid of this nameless variable. And then from there, we just recognize that the total number of liquidity pool tokens that are going to be issued is going to be the sum of these two expressions. And so subbing delta Z sub X and delta Z sub Y for their expressions, and then expanding this out and simplifying, will actually give you the result. So again, I'm skipping some tedious steps here, but there's actually a fairly fast method that Curious found that I thought was pretty good. Then another one of the questions was to, instead of providing liquidity, let's have a look at the case where we're removing liquidity. And it's basically exactly the same method. So we start by redenoting delta Z here, first with sub X, and then creating the next one sub Y, and noting that there is a change here for the this should actually be a negative. Okay, so I apologize for that slide. I just noticed it's got a sign inversion, but that's okay. The overall result should be basically the same, which is, you substitute these two expressions in, and then expand and simplify, and you will end up with this result, which is really nice. Okay, then more importantly, is generating the swap equations. So remember what I said, which is that when Bancor V1 was being developed, there was no sort of industry standard, right? It came before all of the common nomenclature that we use to describe AMMs and bonding curves and everything else. And so whereas today, the explicit focus when we're discussing bonding curves is on the reserve balances inside the pool, the focus in the original documentation surrounding Bancor was more on the interaction between one of the reserves and the liquidity pool token, either that be the price or its issuance or whatever it happens to be. But what I said was that you can get exactly the same result just by piping these things together, right? So provide liquidity in one token to be issued a pool token, and then, take all of those pool tokens and put them back in and redeem that liquidity for the token on the other side of the exchange. So all you need is this expression, which is the one that says if you're adding delta X tokens to the pool's XP reserve, then you receive delta Z tokens in return. And then the opposite, which is withdraw liquidity in a single token, which is you're burning delta Z LP tokens from the total ZT that exist, and then receive delta Y tokens from the pool's YP reserve. Not too difficult. So again, I'm going to take delta Z and add sub X just to make it clear what we're talking about. And then from here, we realize that after we've added liquidity on this side, the delta Z sub X is going to be again added to the total here. So it's no longer just Z sub T, it becomes Z sub T plus delta Z sub X. And because of the way that this formula is constructed in the generic way, notice that we just subtract that delta Z sub X from itself anyway. So this simplifies out very, very quickly. And then all we need to do is take the take the delta Z sub X expression here, sub that in down here, and we get this expression. And then after that, again, just expand and simplify as much as possible. You should be able to get to this this step relatively quickly. And I would have actually accepted this as like a perfect, like this is still a perfect answer. But I find it just a little bit nicer to multiply these exponents together to get to the final result, the one that I show. But again, I think that this is more of like a notational convenience. I have noted that some people prefer to keep this out here so that the radical is implicit rather than is explicit rather than implicit. But whatever, to each their own. Now, once you've figured that one out, the thing that I asked you to think about, this wasn't necessarily a homework question, but something that we kind of ended the last lecture on, and I think is a good place to cover it now, is that if we have this swap equation, can you show that the invariant function that underpins the entire system is equal to this expression? So for this, it's, I think, worthwhile to return to some of the conventions that we defined, because, while the original literature for Bancor uses things like absolute values, which makes some of the math, I think, a little bit easier in some cases, here we're trying to subscribe to the industry conventions. And so what that means is that in general, we try to force delta Y and delta X to always be a positive number. And this is so that we don't end up with like underflow and other potential problems with the smart contracts, including precision loss, because we need to store an extra bit to denote the sign. And so what you need to realize here is that because both of these are positive numbers, and by definition, delta Y is being removed from the pool balance while delta X is always added to the pool balance, then at some time in the future, T1, the amount of X tokens inside the liquidity pool is higher than what it started with. And at some point in the future, the number of Y tokens inside the pool is lower than what it started with. And so this just means that when we're calculating delta Y, it's important to take the amount that the pool started with and subtract the amount that it ended up with. And for delta X, we do the opposite. We take the amount that the pool ended up with and subtract the amount that it started with in order to get these two values. This isn't the only way to solve it, but I think it's the fastest once you've come to that realization, because here we can basically just sub delta Y and delta X for these two expressions, which brings us to here. And then after that, you can see that the XPT0 and XPT0, negative XPT0 negate each other. So you can basically get rid of that, which simplifies down to here. And then after that, all we're going to out this YP at T0 and the part in parentheses, which brings us to this middle expression, which is just, YPT0 minus something is equal to YPT0 minus something. So this means that YPT1 and whatever this is must be the same. And so we just set that equality. And then after that, it's just some, again, tedious steps moving the exponents around. But if you can't see it, all I've done is divide through by YPT0 to get to this step. I've raised both sides to the power of RY, which means that we've got this fraction to the power of RY, and because of the way that exponents operate, we managed then to multiply out this RY and just get straight RX. And then after that, I have moved the powers inside the fraction to get to here. And then the last step is pretty easy. We basically just cross multiply in order to get these out. And what this shows you is that that X in the pool at T0 raised to its reserve weight multiplied by the Y token balance in the pool at time equals 0 to its reserve weight is equal to essentially the same expression, but at the next time interval. And so this means that these, it doesn't matter where you are in time, this result is always equal to this result. So you can just say that the pool balances of each token raised to their respective reserve weights is always going to be equal to some constant. And if you wanted to go one step further, and have a look at the very narrow case where both of these reserve weights are exactly 1/2, then you can derive the famous constant product formula, which was popularized later by Uniswap and others. So that was the end of the homework, and I think, like I said, a really good refresher before we get into a slightly more complicated version of these same things. So recall that we started with with these formulas from the original Bancor patent, and then I showed you how we can convert them using industry nomenclature into the modern convention. Now, because we're moving from 2 dimensions into higher dimensions in this lecture, I'm going to play around with the syntax that we're using just to be able to accommodate an arbitrary number of dimensions, so that we don't run out of letters, or that we start getting conflicts with different variables. So this is one of the swap equations that we introduced. And all I'm going to do here is basically force all of the token balances that we're referring to always be the letter X sub some number, some integer. So it's usually going to be like a 1 or a 2 or a 9, depending on how many dimensions that we're using. And so, this looks, I guess, like a little bit weirder because there are X's all over the place now. But if it helps, just keep in the back of your mind that all we're doing is making it explicit that X is just a generic variable name for a pool balance of some token, and then we always subscript it with some number that denotes which token we're talking about. So delta Y becomes delta XJ, meaning the next token in the line. XP or X sub P becomes X sub P sub I, and Y sub P becomes X sub P sub J. I know that it's not, there are at least a little bit of mental gymnastics here, and I will try to make sure that we keep it relatively slow. And if you find yourself stalling, when you're maybe revising some of these slides later or something like that, just come back to this slide to remind yourself how we do these substitutions. But for the other swap equation, which is to decide how many tokens you want to extract from the pool, and ask the question, how many tokens do I need to provide to the pool in order to achieve that number? Again, we end up with the with the same swap formula that you've seen before, but just substituting for this new subscript nomenclature. I've tried to color code a lot of these formulas on the way through to try and keep it as consistent as I can. But again, if you need me to stop and revise something, just let me know. Octopus.
I want to be sure I haven't missed something important because sometimes notation hides important information.
Sure.
Um, is it accurate to say that primarily what you're doing here is going from an ordered pair to a vector, or is there something more sophisticated than that happening?
Yeah, no, that's a totally reasonable way to say it.
Okay,
You
thank you.
could, yeah. It's basically I'm going from a. It doesn't necessarily. It depends on what you mean by vector. If by vector you just mean a list of stuff, then sure. I might prefer to think of it as a set. But again, referring to the same idea. But yes, we're now referring to a liquidity pool that has an arbitrary number of different token identities, and they're all just kind of in there together. And so we're going to denominate them with whatever subscript we need in order to refer to the thing. But in terms of the algebra, it's not going to matter too much. I just wanted to make sure that people understood why I'm using it this way, because eventually we're going to have to use the large operators, and some of the expressions that we're going to be looking at is just so much easier when you can, when you can index tokens not by their name, but by their position in a list. Is that clear, Octopus?
Yes, very much so. Probably in tuple is better terminology than vector, but I think I understand what you're saying.
Perfect. Okay, so yeah, if you remember this slide from the last lecture, this used to be x and y, but now we're using x sub I and x sub j. And again, I'm going to be using, because we need, I think it helps just to decide that we're always going to be using j in a generic sense to refer to the token that is being extracted from the liquidity pool by the trader, and the subscript I to denote the token that is being added into the liquidity pool by the trader. Which also means that, over time, again, everything here is one-to-one substituted from the XY nomenclature that we saw in the last lecture. But yeah, very, very straightforward, right? If the XI token is one being introduced to the pool, then the user is losing that balance. And so this will be denoted as X sub U sub I. And the J balance of the for the user is always going to be X sub U sub J. And so we're adding delta X. Oh, by the way, I just realized that there's a bit of a redundancy here. The delta X UJ, this would be just as valid without the sub U, because because delta X sub U sub J is exactly the same number as delta X sub P sub J, but otherwise everything is exactly the same. Okay, so this is what we're going to be looking at today, and hopefully you're beginning to see why the new syntax is going to be so helpful. So let's just go through this, because I know that some of this notation is not going to be familiar to everyone, and also that I tend to abuse notation fairly regularly. And so if I'm writing it, in a document, I will just provide a description of what I mean by certain things. But for the sake of this presentation, I'm just going to tell you what it is that I mean. So let's just have a look at the left side first. If you haven't seen this symbol before, this just means for all, right? So all we're saying is that there is a set of reserve weights that's defining our liquidity pool, and each one of them is a number between 0 and 1, and that the sum of all of these numbers is equal to 1. So if we've got 10 tokens inside a liquidity pool and we want to weight each one of them equally, then each one would receive a reserve weight of 0.1. And this satisfies both of these conditions, because now each one of the reserve weights is a number between 0 and 1, and the sum of all of them is equal to 1. As long as that is maintained, then it's going to be much easier for us to make sure that we're referring to the same ideas as we progress. One of the things that I did say in the last lecture is that this is not strictly a requirement for expressing swaps, but it is really important when it comes to liquidity provision and removal to avoid, giving people unfair advantages or disadvantages compared to other users in the pool, depending on whether or not they came early or late. For the reserve invariant component, all we're saying is that for all of the token balances inside a liquidity pool, it must be a positive number. It can never be 0. And this, in a way, I think is self-evident. We know, I think, just from our familiarity with, the constant product curve, that it is asymptotic at the X and Y axis, meaning that you can never actually drive a token balance to zero. And certainly, you can't create a liquidity pool with a negative token balance, or you shouldn't be able to create a liquidity pool with a negative token balance. And while it's possible that there may be, AMM designs in the future that allow for negative balances, if, for example, if it's supposed to represent a loan or some other value, that's okay. But in the context of the discussion that we're having, just know that all of the token balances must be, a positive real number and cannot be zero. Then the expression that we're looking at is just that the product of all of the tokens. So for each token inside the liquidity pool, raised to its respective reserve weighting is equal to some constant. And you saw that we came to this conclusion from that last homework question. It was something that I just stated in the last time that we spoke. So I went back over some of the things that I said in the last lecture, and I realized that one of the concepts that I think is probably the most important concept with respect to what a liquidity pool is, what its value is, how it operates, and what the set of the liquidity pool smart contract, the pool token, the oracle price, and all of these things, what they mean together. And so I did this by sort of asking off the cuff a question about a pool containing ETH and USDC, and can you insure it through the price? And people could, but I think it missed something really important. So now we're going to be exploring that situation, but now in 3 dimensions instead of 2. So this is what I was talking about. When we're talking about a liquidity pool and the liquidity pool token that it represents, or that represents it, we're always referring to a portfolio of some value. And in a way, as the industry has gravitated towards bonding curves as being the invariant function or the implicit curve of some function that denotes the token balances inside the liquidity pool, we've kind of forgotten, or at least it's become a little bit more obscured, that the underlying device is still a rebalancing portfolio. And it rebalances according to a very specific intent by the person who created it. So for example, you could say that for a portfolio of 3 tokens, A, B, and C, we want 1/4 of the portfolio to be denoted exclusively in A tokens. And then after that, we could say that we want 1/8 of the portfolio to be denoted exclusively in B tokens. And after that, we could say that we want 5/8 of the portfolio value to be denoted in C tokens. Now, if that portfolio, let's say that we know something about that portfolio already, either because we've interrogated it or someone's just told us, it doesn't really matter. Let's just say that the portfolio is known to be worth $1,000. The important thing here, the real take-home message, I think, from all 3 of the lectures that we're going to be discussing, is that we're trying to say something about not how many tokens there are, but what they're worth. So if you know the portfolio is worth $1,000, given that 1/4 of the portfolio is always denoted in A tokens, you know that there's exactly $250 worth of A tokens. Now, this could be 1 A token, it could be 0.1 A tokens, it could be 1 trillion A tokens, right? It doesn't matter how many there are. All that matters is they represent 1/4 of the total portfolio value. For B, right, if we know that there's 1/8 of the portfolio is denoted in B, and the portfolio is worth 1,000, then there must be $125 worth of B tokens. Again, doesn't tell you how many B tokens, it only tells you what they're worth. Last but not least, the majority of our portfolio is denoted in C tokens, and 5/8 times 1,000 is 625. So to harp on that message, and for the benefit of repetition, we are not really interested in how many tokens there are. This is kind of the mistake, I think, that people make the first time they come to analyze AMMs and bonding curves. We're much more interested in how they compose the portfolio. And I think that the reason why this is often overlooked is because it's a much more sort of nuanced way to examine the system, right? And it's in a way, it's inconveniently complicated, because now you're left wondering, well, how do you even do this, right? How can you come up with a system that no matter what is always representing a certain proportion of the portfolio that it represents in itself? And this is where the Bancor formula came from, right? If we take just the sum of the A tokens that there are and raise it to the power of a quarter, and we take the sum of the B tokens that there are and raise it to the power of an eighth, and take the sum of the C tokens, raise it to the power of 5/8, this will always be some constant value. And this is where those, X1 and R1 is coming from. We're really just decomposing the things that are inside the liquidity pool and pushing it together into this expression. And this is the thing that causes the portfolio to maintain an adherence to the portfolio weights that the user has nominated. And maybe that's surprising, right? If you've never thought of an AMM as having that property, then I encourage you again to reconsider the situation that I brought up in the last lecture, which is that I said that Uniswap Uniswap V2 is a 50-50 weighted, Bancor V1 liquidity pool. And if we've got some ETH in there and some USDC in there, and we know the price of both of them, remember, you even intuitively know that at any time when you withdraw your liquidity from Uniswap, exactly half of its value is going to be denominated in ETH, and exactly half of its value is going to be denominated in USDC, or that the total amount of USDC in the liquidity pool is equal in value to the total amount of ETH in the pool. And that's true no matter what, right? Even if neither one of those tokens is being denominated in the other. So, for example, you could have a compound Aave liquidity pool on Uniswap V2. And even then, right, you know that when you withdraw the liquidity from there, the dollar value of the Aave and the dollar value of the compound is going to be equal, even though dollars isn't even a part of the bonding curve. And that is, I think, the most interesting or the most surprising result of the entire AMM space. And it was also the seminal part, right? And it's kind of sad that I think that has been forgotten. And so it's my pleasure, I think, to speak to you all and sort of bring attention back to that property, because it's absolutely not trivial. Okay, so that explains what these R's mean and sort of why we're listing them the way that we have. So in the in the case of a 3-token pool, we would have R1, R2, and R3. And we would have, XP1, XP2, and XP3. But it's not limited there. We can go up to any number of tokens that we want, and whatever we choose R to be, right, that will always be the total value proportion of the portfolio that it represents. So these are kind of the key formulas. Now re-indexed to get rid of the X and Y and other things, and instead use our large operator nomenclature in order to make things a little bit easier. So again, you can, if you need to categorize these ideas in your head, just remember that you can deal with exclusively the reserve invariant, meaning the way that the liquidity is constructed inside the pool. You can have a look at the way that the liquidity pool token interacts with the user who is providing or removing liquidity from that pool. Or you can also have a look at how one token is exchanged for the other token and does not involve an LP token intermediate. And all three of these things are absolutely valid ways of examining what I consider to be sort of the object of a bonding curve or of an AMM. And neither one of them is I would say more right than the other. They're all sort of equally helpful perspectives on the same mathematical concept. And so to sort of focus just on the swaps, I think sort of is to deprive yourself of a much deeper understanding of how these things behave. So as we move into n dimensions, as I said before, it becomes much more difficult to visualize things. And this is problematic, but it's not unachievable. So the two-dimensional representation of a bonding curve with only two tokens is trivial. And luckily, 3 dimensions isn't too bad. This is what's called a cross-eye stereogram. And you can try this. It doesn't work for everyone. It's a type of optical illusion. But the idea is that if you allow your eyes to go cross-eyed and then focus both of these images in the center, it will actually produce a 3D image for you that kind of mimics depth, similar to what AR or VR would give you. So this is one possible way to do it. You can also, draw a 3D curve, in any of these dimensions that you have. And maybe this is a better way to do it. And what I find, though, is that people generally don't really have a good grasp on what the shape of these things is until they have a way to interact with it. And so what I'm going to show you is exactly what that looks like here. Can you see this? Can you see my notebook?
Yes, very clear, Mark. Thanks for sharing this. This is so exciting.
Perfect.
I love when we go to Jupiter.
Okay, so what we've got here is I've created a bonding curve with 5 different assets in it, and I've just labeled them A, B, C, D, and E. And you can see here that I'm asking just to see the ABC slice. And so now we've got this plotly plot, and you can see that if I get close, it has this wonderful property of being able to sort of draw these contour lines across its surface. And it's important to realize that wherever we are on this plot, you can actually get a gradient from any direction, right? What we're really looking at when we've got more than 3 assets in a pool is that when there's when we're trying to quote a price, you can either quote the price always in one asset versus a different asset in the pool, which I think is that's a very, very helpful way to do it. It kind of keeps things nice and reasonable. But in some higher math, it's also possible to quote like the direction of one token with respect to 2 other tokens, or the opposite, right? What 2 tokens is worth at the same time compared to 1 token. And you can sort of compose and decompose these things together as you go. But it's important to remember when we're, every time we're looking at, one of these bonding surfaces, this is still just a 3-dimensional slice of a hyper object. So you can see here, I think, this is in dimensions A, B, and C. But then we get it looks the same because it's always scaling it to a cube, but this is now dimensions A, B, and E. And the thing to realize, I think, that's going to sort of, I hope, make it a little bit easier to understand, is that even though the A and B dimensions are exactly the same, the C dimension in the top one is scaling, is going off the scale at around 700, whereas in E, it's already going off the scale at half that value. So the rate at which the gradient changes can be much faster or much slower depending on the reserve weight, right? The only difference between these 2 things is that the reserve ratio of C is 0.3, whereas the reserve ratio of E is half that. So it's no it's no coincidence that the E dimension scale is half of what the C dimension scale is, which is coming back to something that Octopus asked me about last week, which is just the fact that no matter what hyperbola you're drawing, anything that has this kind of power sequence could always be stretched and squished in order to give you the same shape again, just by rescaling the axes. And just to sort of make the point perfectly clear, here is one with dimensions C, D, and A, and it looks like the same shape. But you can see that now we've got the C dimension on one scale, the D dimension on the other, and now the A dimension is coming off the Z here and ending at 400. So you can gain, I think, a better appreciation for how these things work. Also seeing them, and I've got to remember how to do this, but there is a way, I think, in Plotly where you can, rather than force everything into a cube, you can say, let everything be on natural scale so that all of the ticks or the tick spacing matches up. And then you can really see that you can get sort of this distorted looking, squashed or rescaled hyperbola shape, which is quite nice. Okay. Okay. So recall then that we're talking about portfolio weights, right? That we are these reserve weight numbers that we're choosing are always going to be how much of the portfolio is denominated in that token, no matter how we measure the portfolio's value. So this $1,000 here I chose for convenience, but this could just as easily have been Bitcoin or ETH or tomatoes or secondhand cars. Whatever denomination we choose, we can still split the portfolio this way, even if whatever that thing that we're denominating it in isn't present in the portfolio itself. So let's think now about market equilibration and rate dynamics in light of some of this new information. So I'm going to introduce. I don't think that this is standard. I just made this up, but I'm going to introduce some new syntax here so that we can describe the prices of things, I think, in a more mathematically concise way, or at least a way that is more amenable to things like dimension analysis or unit analysis, if you prefer. So let P be the price of something. Right. So, for example, let it be like the Oracle price. And I've stated here that an Oracle, don't let this infer that an Oracle network is needed, like Chainlink or something similar. Just that there is, some knowledge somewhere in the market that the prices of what the prices of these things are in whatever we're trying to denominate them in. Usually, the best oracles are arbitrageurs. So the way that I'm going to define the price of something is that whatever that token's identity is, right? If this is BNT or Gearbox or whatever it happens to be, I'm going to let the price be denominated such that it's the number of that token that you get per US dollar. Right. So, in this instance, if we want to get P ETH and ETH is $2,000, then the P value here will have a value of 1/2000, but the units will be ETH per USD, right? And similarly for Bitcoin, if Bitcoin is 20,000, then this P value is going to be the reciprocal of 20,000, but the units will be BTC per USD. And again, this is just convention. I could have chosen to do it the other way around, which would be, in general, I think the way that finance does it, right? So for when you're looking up the price of ETH, you generally don't think of how many US dollars or how many ETH are equivalent to $1 US, but you think of it the other way. How many US dollars are equivalent to 1 ETH? So this inversion is something that I find, has baffled like a lot of people that come to AMMs and start developing. But it turns out that this is also true of like Forex desks and things. This is a very common mistake. And so, if you think that it's sort of overkill or, redundant to claim or to define exactly what I mean by the price of an asset, just know that, flipping these fractions upside down is, I think, probably one of the greatest bottlenecks in DeFi development when it comes to defining the way that smart contracts should work and things like that. Okay, so what this means is that if we know the Oracle price for two different assets, right, I and J, and we know that we want the marginal price to, to be equal to the ratio of these two prices, and we know that the marginal price formula is equal to this, then it's possible to derive an expression that will allow us to calculate the coordinates of any asset in any number of dimensions just by knowing those oracle prices. So, for example, PI over PJ might be something like PETH over PBTC. And you can see here why I've chosen to quote the price the way that I have. So rather than the price of ETH be 2,000, letting it be 1 over 2,000 means that it's much more it's much easier to work with these fractions without having to sort of remember when you're supposed to take the reciprocal of something or whatever. So here, we're looking at the number of, we're trying to basically calculate how many ETH are there per BTC. And you can see that, just by glancing at these numbers, that we need at least 10 ETH to be equal to 1 BTC. Whereas if we had quoted these things upside down, we would end up with a slightly weirder number. And over here, these things would be sort of back to front. So quoting them this way means that we can calculate this number very easily. So this is where the convention comes from. But this is important, right? That if you've got PI and PJ and you've got access to Oracle prices for both of those assets, and it doesn't have to be in dollars, it could be in euros or ETH or Bitcoin or whatever it happens to be. As long as you can organize the price quotes this way, you can generate a marginal price for one token versus the other. And this is where the market dynamics of AMM start to get a little bit more interesting. And this is the formula that allows you to calculate the exact coordinates of any asset inside the liquidity pool using only those Oracle numbers. And this equation you will not find published anywhere. I'm not sure if this is a deliberately kept secret, but I've often spoken to people that are trying to perform arbitrage on, the Bancor V1 contracts don't really, they're largely deprecated, but Balancer is one of the, one of the projects that continues to use the Bancor formula. And so I'm often contacted or have to, advise other projects on how they can effectively arbitrage that system. Because they might be creating something like an index fund, or they might be creating liquidity in sort of the bootstrappy way, the 2080 pool versus maybe a couple of other things to kind of keep the price stable. And after that's set up, they often complain that the balancer pools will fall out of agreement with the rest of the DeFi ecosystem, right? Things like Uniswap V2 or Uniswap V3. And the reason is that it is very, very easy to derive the arbitrage formulas for Uniswap V1 and V2 and V3. Whereas the balancer system, where you've got n dimensions, you can't swap any one asset without changing the prices of every other asset. And that is what we're going to look at right now. So imagine that we create a liquidity pool with these 5 assets, A, B, C, D, and E. And we've got, the reserve balances here. We've got their reserve ratios. And I've just made up some Oracle prices. There's nothing special about these numbers. I've got them in red because I've deliberately made sure that these prices don't match the marginal rates between any of these assets. And if you want to verify that for yourself, this is the exchange rate matrix. And the way to read this is always, it's the row, the column name over the row name. So, if you want to know the exchange rate of A per B, exactly the same way that we had it before, then it's always the column, A over B is equal to 0.5, meaning the price of A over the price of B is equal to 0.5. And remembering that it's the reciprocal of the price that you would usually consider. So let's just go through a quick example here. If the price of A over the price of B is equal to 0.5, then this means that there are twice as many A tokens. This means that there are twice as many B tokens per numeraire than there are A tokens per numeraire. And so, if we're looking at, a stable coin that is worth $2 versus a regular stable coin that's worth $1, then it would be the B token would be the $1 one, right? Because it's going to be twice as many A tokens, twice as many B tokens. Make sure I get that around the right way. Conventionally, or using traditional arbitrage, traditional financial intuition, we would assume that if the price of A over the price of B is equal to 0.5, then we would think that means B is $2 and A is $1, right? But the reverse is true here, because we're not quoting it in dollars per A, we're quoting it in A per dollar. So it's actually A is the $2 coin and B would be the $1 coin. And you can see, obviously, because of the way that we're quoting this, it's ones down the diagonal, because we're always comparing A to A, B to B, and so forth. So if you want to know the price of A in B, or the price of A in C or D or E, then these are all the numbers that we get just by applying that marginal price formula. This is coming directly from the expressions that we looked at both in the last lecture and have looked at in slightly more detail in this one. So this is the interesting step, right? How do you make sure that all of the pool balances, after swapping tokens with other tokens, eventually agree with those oracle prices? Octopus.
I don't mean to derail you.
No, go ahead.
Yeah, I was going to ask. So I've seen a lot where people have a matrix of prices and then they run it through a graph theory algorithm called Bellman-Ford to search for arbitrage cycles or profitable arbitrage cycles. Is the convention that you've chosen compatible with that, or do I need to flip it back before?
Yeah, I mean, I'm not super familiar with that algorithm, honestly. You're right. So there are a number of them, including things like like convex optimization, I think is one. It depends on whether or not you're doing it between liquidity pools or within a liquidity pool.
Okay.
Right. So between liquidity pools means that you need to take into account the fact that they're going to be different sizes. And this can complicate things. And in general, that's where convex optimization is your best friend. But actually, our chief economist has come up with one that's slightly faster and a little bit more numerically stable, that we call the marginal price method. We haven't published it yet, but we're going to. Like, we're not keeping this stuff secret. We'll let you know when it's out. But the thing that I'm trying to pay attention to with these slides is that let's just assume that there is only one liquidity pool all by itself. And it's got all of these different tokens in it. And it doesn't exist in a vacuum, right? It still exists in the context of the rest of the market, of third-party participants. And those third-party participants will act, or are incentivized to act in such a way so as to make sure that our portfolio composition is equal to, or its value composition is equal to the reserve weights that the user chose when they created the liquidity pool in the first place. So in our situation, because it is just the single liquidity pool, you can just use this expression to calculate the exact coordinates of each of the tokens. There is hardly any need for anything more. There just isn't any need for anything more sophisticated than this, because it's deterministic from the outset. I should point out that even what I'm showing you today, even though it is slightly complicated, it actually gets more complicated because so far we haven't really considered how fees change the price quote for things and what it even means to have a balanced liquidity pool in the, when there is a cost to the user to interacting with it. But this is something that I was hoping that we would explore next time. So long-winded explanation, but the point is that yes, you're right. There are lots of arbitrage methods out there and algorithms, some better than others, some faster, some more numerically stable, and so on. Those ones are generally optimized to perform arbitrage between different sources of liquidity when they don't necessarily have the same size. Today, we're only looking at performing arbitrage within the same liquidity pool, which means that we don't need anything too fancy, and you can just use an algebraic method to solve it.
I see, because there's no differing opinions about, or there's a single source of truth about price in this instance.
Yeah, exactly. And this is kind of, if we go back just a second. Oh, no, wait. Forward, my mistake. Yeah, this is why the choice of the word like oracle price is not incidental, right? We are literally saying that we know for a fact that this is the price of these things in dollars, and so we assume that someone is gonna has access to either an infinite source of liquidity somewhere else, or just that there is someone in the market who is either interested in exiting from a position so long as they get a price better than the market rate, or that there's someone who wants to enter into a position or is encouraged to enter into a position so long as they're getting a better than market rate trade. And these assumptions have turned out to be pretty good. I think in the very, very beginning, there wasn't even that much traction on Ethereum, right? Back in 2017 when Bancor was released. But within a couple of weeks, there was a very large number of sophisticated arbitrage bots and things that were already swapping and rebalancing the pool, usually interfacing with something like Binance or back then it was probably Bitfinex, but whatever. The point that I'm trying to make is that the people that interact with the liquidity pool are almost a part of the liquidity pool's system, right? It is the heat, that causes the or maybe it's the liquidity pool that is the heater that loses heat to the ecosystem. But whatever your perspective is, the liquidity pool by itself and all of the equations and things that define it, the only reason they work is because eventually someone is selfishly motivated to interact with the liquidity pool, so long as it's bringing that liquidity pool into balance with the market expectation.
Thank you. That's really helpful.
My pleasure. Okay. So yeah, those are the exchange rates. Then this is the instructions, if you like. Oh, MD, go ahead.
Thanks, Mark. Great job so far. Before we go on, could I just ask a question regarding this topic and see if we could attach it to like a traditional finance scenario?
Mm-hmm.
So like you've referenced index funds or ETFs, and you've referenced portfolios, which is really cool because to think of things as a portfolio, I think is pretty intelligent kind of viewpoint or lens to look at this stuff. But if you look at a portfolio of stocks held in a basket, and a user, a holder of that basket has like a token that represents the composition. So in your case here, it's a 3-token model. So the LP token represents the composition of these 3, correct, Mark? You've been sharing that.
Yeah.
Right. So then, So I guess what I'm saying is, technically, if a request comes in for redemption in an ETF, the structure can choose what to sell to fulfill the redemption. Whereas in this scenario, the equation is fulfilling that request for redemption automatically. Is that fair to say?
Yes, that is absolutely fair to say. Yeah. So in this situation, if so you're right. So if you've got a a managed fund that has created the index, and you are trying to redeem for like dollars or something like that, it could be, by the way, that part of that index includes dollars in it, but often it's just composed of different stocks. Now, when you say that you want to redeem, it's almost always the case that you want cash, not some of the stock in that portfolio. And so then the fund manager is going to be the one that is tasked with determining how the which stocks are going to be the ones that get sold in order for this person to withdraw their value. And that's going to be influenced by a whole bunch of different things, right? Including including market liquidity and other and other effects. You could actually do this with an AMM, and in fact, there was someone that I advised recently who's doing exactly this structure, where instead of liquidity withdrawals being like instantaneous, there would be like a holding period, and it would be settled at like the end of each week. But at the time that you choose to withdraw, the value of your position is preserved. So if you withdraw today for $1,000, by week's end, that will be what you're delivered. And a lot of a lot of ETFs actually do have that same sort of holding period. You can't necessarily withdraw very large amounts instantaneously. That you have to wait for things to clear and that kind of thing. The problem with cryptocurrency is that if you are trying to do that as a DeFi project, depending on where you're regulated, you will very, very quickly find that your legal exposure becomes profound. So even, so I'm more familiar with the Swiss regulation, but in this particular instance, if one of the developers had to decide, which tokens are going to be sold and for what and how long that's going to take and that kind of thing, we would become both a financial services provider and I think a financial intermediary. And we would need to apply for all kinds of financial licenses in order to offer that kind of product. And so this is why this is why a lot of DeFi protocols are built in such a way that the way that it operates is exclusively under the user's choice. And so you're right to observe that if someone's withdrawing exclusively from like token A, then the value of their position is going to slip a little bit, and so they won't quite get if let's say that they owned 50% of this liquidity pool, they wouldn't quite get $125. They would get some number slightly less than that. But they also have the option, right, to withdraw in A and B, or A and B and C, and in any ratio. And so in a way, you're taking the decision making that the financial professional would make, and you're giving those decisions to the user. And in a sense, that is exactly what DeFi was supposed to do, right? Is to take all of the, the incumbency, all of the middlemen that kind of make decisions on your behalf, and tell people you can make the decision now. Now, there's a problem with that, which is that it assumes some level of financial literacy, which is generally a very bad assumption, especially in DeFi for some reason. But that is kind of the ethos, right? It's it's a very libertarian point of view. And with that in mind, you have to remember that the opposite side of that coin is that everyone has a democratic right to fail, or a democratic right to make a bad decision. Whereas traditionally, financial regulation is to protect people against bad decisions. DeFi is you have the right to make a bad decision.
Oh, thanks a lot, Mark. I just see it as just another example of like how the designs are are kind of morphed from, there's like a certain framework from traditional finance that you can bridge over to DeFi, and then, you adjust it for DeFi. And so,
right.
Yeah. And actually it gives kind of creativity and like even hope in the sense that I do believe that the Lego pieces will and might even already be here to build something like this if you were so adventurous, but that's for another day. Thank you.
You're very welcome. And you're right. Certainly some of those pieces exist. The ones that are the most compelling are the ones that preserve anonymity of the person who's doing the management. And this is, I mean, it's fine, but it completely flies in the face of like the trustless narrative of blockchains and DeFi. Because as soon as you are allowing someone that you don't know, who no one knows, the ability to manage funds on your behalf, the failure rate is going to be extremely high. And, in a way, this is what DeFi has become known for, right? Is strangers trusting their money to other strangers, and those, trustees essentially taking off into the sunset with it. So I think that the way that, you're right to observe that the pieces are here, but what they don't account for is the ill will of humans towards each other in general, or the greed of humans, or the affinity of humans in DeFi specifically for financial crime. And this is where I'm getting, like, I am actually quite interested in in cooperating with regulators and bringing in like institutions that have some sort of that will experience some sort of legal ramification to if they behave badly, and then we can start to develop some of these some of these products that you're talking about. But yeah, the challenge has always been, how do you do it without trusting anyone and without anyone having to manage anything, and giving the user the full responsibility of the protocol. And in a way, I think that the best product market fit is to treat that as one extreme and then treat traditional finance as the other extreme, and that DeFi can represent something that's kind of in the middle. So bringing in, licensed, trustworthy institutions to make decisions on users' behalf, I don't think is too much of a compromise.
Well, in a weird way, we're seeing this kind of, and I don't want to stop you because I want to respect your presentation, but these automated liquidity management providers now, Mark,
correct,
where you have these protocols that are managing people's LPs in the most optimal way because of the new Uniswaps like V3, where you can have a narrow or wide band of liquidity and stuff, and sometimes your tokens get out of whack because of some market movement. But now there's actually protocols that are just they're doing that for users. Anyways, thanks.
Yeah, you're welcome. The important thing to realize about even those ones is that there's usually some off-chain component. There might be, like, someone can correct me if I'm wrong, there could be a liquidity management solution that's entirely on-chain, in which case, I think that we're already there. It's not just that we've got all the pieces, but they might actually be already assembled and functioning. But of the ones that I'm aware of, there's always some kind of off-chain component, whether it be the logic that performs the rebalance or something else. So it's not quite it's in that sense, it's like, is it even still DeFi? But whatever, it's there's clearly a market for it, and so I don't mind if the industry is heading towards that direction. Okay, where were we? Okay, so let me. There was a bit of a tangent, so let's just remind ourselves where we're up to. And this is that I've told you what I mean when I say the price of ETH is 1/2000, right? That means that the price of ETH is $2,000, but I'm going to quote it as ETH per dollar, not dollars per ETH. And if you allow for that, let's say counterintuitive way of quoting a price, then at least you can come up with a very, very nice formula that that allows you to rebalance a pool in any number of dimensions. And so to demonstrate that this is possible, we're creating a liquidity pool here with just generic tokens A, B, C, D, and E. We've given them some reserve balance here. We've given it some reserve ratio, and we have quoted the Oracle prices here, largely at random. So none of these Oracle prices, I think, really line up with any of the exchange rates that you would expect between any of these tokens. And this is the exchange rate matrix to show you exactly what those exchange rates are. And so as you go through the Oracle prices, you may find that some of them agree and some of them don't. But the point is that this pool is out of balance, and we want to calculate exactly what the swaps should be in order to rebalance it. And so now we're kind of stepping out of the protocol. Out of the protocol side of things, and now into the shoes of someone who is interacting with the protocol as a trader for the explicit purpose of selfishly trading against the liquidity pool in order to turn themselves a profit, right? And as they do that, it should bring the balance of all of the tokens into such a state that the portfolio valuation is deconstructed in exactly according to the reserve weights. So this is that instruction set. We start by swapping 3.7-ish of the E token for 16 of the A token. We then swap 2.8-ish of the D token for 5.07 B tokens. We then swap 2.5 C tokens for 3.19 B tokens. And then these two B tokens that we've accumulated, we keep some of that and we swap the rest for 1.7 of the A token. And after we've done that, you'll see that these are the new reserve balances. So quite away from where we started. The reserve ratios have obviously not changed, and the Oracle prices now perfectly agree with the state of this liquidity pool. And so the exchange rate table now looks quite different, but that's good, right? We expected that. Okay. Yeah, we're up about 75 minutes. So this is roughly where I wanted to end things. But I have a little bit of homework before we begin the next lecture next week, and that is to assume that after having completed this arbitrage step, exactly the way that we just did. Assume then that the Oracle then quotes all of these tokens as being exactly $1. What are the steps that you would need to take in order to rebalance that pool? And this is, I think, it's at least slightly more involved, but there's nothing that you have to, I think, deduce here. This is mostly about applying some of the theory that I've already provided here. And then there's a couple of other things that you might want to do while you're there. For example, after you've rebalanced the pool and everything is at $1, can you confirm for yourself that however many A tokens there are, multiplied by $1, is that equal to exactly 20% of the overall portfolio value itself? And confirm everything that I've stated along the way. But yeah, so I did have much greater ambitions for this lecture. I wanted to show you what concentrated liquidity looks like. So I think I'll save that for the next lecture, which might mean that either we bump some of the stable swap curves, which is something I don't want to do because I think that this group will find that sort of material to be pretty interesting. So either I'll try and see if I can compose this all together into sort of one coherent story, but more likely I'll probably just ask Curious if he'll allow me to add one more lecture to the set, and I'll try and keep it I'll try and keep that one relatively short. But yeah, so this is that concludes the talk for today. So you now basically know everything there is to know, I think, about Bancor V1, which includes everything that Balancer does. And you know, in a way, that also includes everything that Uniswap V1 does, everything that Uniswap V2 does, and everything that, you know, the original Trader Joe does, everything that SushiSwap does. Like, this is a fairly comprehensive you know, summary of like where AMMs and bonding curves and liquidity pools got started. The notable exceptions are obviously Uniswap v3, which is an extension of Bancor v2, and I'll show you that in the next lecture. Dodo is completely unique, and Curve is also completely unique. There are some examples of some other like exotic bonding curves around, such as like, you know, the solidly stable swap bonding curve and other things. But we'll examine these along the way. The point is that by the end of this lecture, you've now been sort of introduced to the theory that describes, you know, something like 90% of you know, of all AMMs on Ethereum today. So thank you for your attention, and I'm happy to answer any more questions if there are any.
I have a question. I thought about DMing it to you, but I think I'll err on the side of transparency.
Sure.
So for the property, so I wish I could remember the source. I've seen papers that try to define constant function market maker in a very mathematical way. One of the properties, and there are different properties they propose, like homogeneous, homothetic, blah, blah, blah. But it struck me that when you were talking about you could rescale it, that I think that that's the geometric interpretation those definitions are trying to get to. Do you have a geometric way in which you think about this, that, you know, being able to rescale it? Or I don't have a very coherent question, but
yeah. So the weights, yeah, there is a very, very helpful geometric intuition. And there's a YouTuber called Mythologer, who's I think he's a professor of mathematics at Monash University, actually not far from where I live. And he had a video recently that was looking at like essentially the property of a hyperbola, right? Or this very specific property of a hyperbola, which is like, it's the only shape that no matter how you stretch it, you can always like compress it in the other direction and it will like equal itself. And so in that sense, this rescaling is like, it's almost like wrapping a token. So for example, imagine that we had, you know, imagine that the price of Bitcoin was like relatively stable at 20K. And the price of Ethereum was relatively stable at 2K. We could, you know, and then imagine that, you know, we wanted to create a way to make markets with these things, but for some reason our OCD, you know, required us to provide, you know, the same number of Bitcoin and, you know, the other asset at the same time to the liquidity pool. So under this, like, obviously ridiculous situation, right? No one cares how many, you know, tokens you provide to the pool in the first instance. But you could imagine a case where someone insists that not only do the values have to be the same, but the actual number of tokens that you're providing also have to be the same. Okay. What could we do? We could create like a wrapping contract where you take 10 ETH and wrap them together, and it issues exactly one like 10x ETH. And so that means that one 10x ETH in our case is equal to one BTC, right? They're now both worth $20,000 each. And then we create our liquidity pool that way. We could also, like, in a way, this is the like one of the heuristics that you can apply to help understand like how the reserve weights are functioning. Because what you could also do is just say that the scale of the Bitcoin component is 1/10 that of the ETH component. And so we can actually skip the wrapping contract altogether and just change the weight of Bitcoin to be what 0.90909, and the weight of ETH to be 1 minus that. And then we would also be providing an equal number of BTC and ETH, but their exchange rate would still be, the Bitcoin is 10 times more expensive than ETH. So that's, I'm not sure if I'm really sort of explaining it very well, but that's the geometric sort of intuition that I want you to have. You really are just like compressing the hyperbola on one side and stretching it on the other side, such that the number of tokens that you can add to the pool is arbitrary, but it gives you the same control over the exchange rate, so that when you create the pool, there are no arbitrage instances available.
Well, I like that idea. So could you either spell or say slowly the name of the channel on YouTube again?
I'll send it to you. It's Mathologer. So Mathologer. I'll find the exact video. I saw it maybe 2 or 3 weeks ago. But I'll find it. I'll send it to you on Telegram.
I will editorialize briefly and say I like that idea. I like that idea so much more than the intuition I had before, which was that this came from solving a differential equation for spot price. I like your interpretation so much better.
Thank you. I'm glad. Like, I hope that it's not that you just like it better, but that in a way it's more useful. Like it kind of gives you a it's almost like when you find a new shortcut key or something on Windows that you didn't know was there before, and now the operating system is just that much more powerful. I feel like the way of thinking about these things as portfolios rather than just price quoting machines. You realize that there's actually a lot of sophistication to this thing. Like it's a very like complicated, but also very, very powerful machine. And the math that we're looking at here is again, like it intimidates some people, but remember you can decompose it down to just these 3 equations, right? This is all you need to describe everything that we've looked at over the last 2 lectures. Which I think it's a beautifully reductionist way of examining what is absolutely a very complicated system. Cool. All right. Well, we're coming up on an hour and a half. I know that for many of you it's very late, so I'm happy to end the lecture here unless there's any more questions.
Thank you, Mark. I want to thank you for your time. Rabbit messaged me. He's in India. It's quite late. He said he might doze off. He's probably dreaming of bonding curves right now. So I want to thank you for your time. And this was incredible. I really appreciate this presentation, and so looking forward to the next one. And if we do a part 4, that's even more exciting. So
okay. Well, I'll see you guys next week. Thank you.
Thanks, everyone, for joining.
Have a good day, everyone.
Thank you, Mark. Thanks, everyone.
Mark.
Fascinating
Thanks,
stuff.
Mark.